Good evening, good afternoon, good morning from wherever you are in the world. I hope you're all happy and healthy. My name is Luke. I'm a producer here at How To Academy, and welcome to what I'm sure is going to be an extremely interesting event. Today we are joined by Marcus du Sautoy, Professor of Mathematics at the University of Oxford, Fellow of the Royal Society, and Simonyi Chair for the Public Understanding of Science. He has presented numerous radio and TV programs, has worked with, among others, the Royal Opera House and Glastonbury Festival to help bring science and maths alive, and his new book, Thinking Better, The Art of the Shortcut, is out now. And that is, of course, why you are all here today, to learn from an expert about how maths can help us unlock shortcuts to creativity, understand algorithms we use every day, and even determine the scale of the universe. So after a 40 or so minute lecture, Marcus will take questions from you, the audience. So please type any you have in the little Q&A function, wherever it is on your screen. Well, that's more than enough from me. So without further ado, it is my absolute pleasure to welcome Marcus du Sautoy. Marcus, over to you.
Great. Well, it's wonderful to be with the How To Academy again. I always enjoy sharing my how-tos with you. And today, as Luke said, I'm going to be giving you a guide through this new book that I've written, Thinking Better, The Art of the Shortcut. And I've prepared a kind of journey for us to explore the shortcut. And I'm going to share my screen with you. So hopefully this pulls up a kind of a map of where I'm going to take you on tonight's journey. And I'm kind of excited to be doing this tonight because it's really the first time I've taken an audience on this journey through the book. So I hope you feel excited about being the first to kind of experience some of the shortcuts ahead. Just to say, sharing screens and things in Zoom and these kind of platforms, I think you can resize me if you feel I'm too small on your screen, or resize the screen I've shared with you. But hopefully you can set things up so you can enjoy the journey. And this journey, I'm going to give you really a choice. To get to your destination, there's the long way, the way that takes a huge amount of effort, plodding along, days, perhaps weeks to get to your destination. It's just a lot of hard work, maybe some dangers out there, maybe things that will mean your journey goes wrong and you don't actually get to your destination. However, there is an alternative. There is a shortcut available. And this shortcut is going to get you to your destination much more efficiently, quickly, without too much energy use, maybe quite an exciting little journey. It's going to require you, though, to be using a little bit of cunning, bit of thinking better, a bit of using your nous to find some clever way to get to your destination. So I'm going to be encouraging you to take the shortcut, and that's really the subject of this new book that I've written, which is Thinking Better, The Art of the Shortcut. And this book is really a celebration of my own subject of mathematics as really the art of the shortcut. Mathematics is somehow a suite of clever ways of thinking that instead of having to do a huge amount of hard work, just plodding through rather boring, it gives you a new way of looking at a problem, and perhaps a way to get to your destination quickly so you can get on with what you really want to do. And I guess actually I was a very lazy teenager as a kid, and I was always happy to look out for a shortcut and how to finish my homework quickly or get to solve a problem as quickly as I could. So I was really excited when, as a teenager, about 12 or 13, my maths teacher at school told us this story during the maths lesson, which really illustrated to me the power of mathematics really as a subject which tries to avoid doing hard work rather than actually trying to do a lot of hard calculations. And it's a story about a young boy. This is Karl Friedrich Gauss, obviously a little bit older than he was at school, but he was 9-10-year-old at school, and he had rather a hard taskmaster as a teacher. And in one lesson, the teacher decided that he wanted to try and get a bit of a sleep, and he set this class this exercise which he thought would take the class a huge amount of time and he'd be able to get a little bit of rest. So he challenged the class very famously with this task of adding up the numbers from 1 to 100. So the hard way to do this is to just start with 1 plus 2 plus 3 plus 4. It's going to take you quite a long time to do this arithmetic on your little chalkboard that they had at school. Probably make a lot of mistakes on the way, fall by the wayside. Are you really going to get the right answer doing it that long way? So Herr Buttner, the teacher, thought, well, this will just keep them busy for some time so I can get a little bit of rest. However, before he even finished setting the task, the young Gauss had written down the number on his chalkboard and slammed it down on the teacher's desk. The teacher was shocked and thought this impudent young man just putting some random number down. So eventually the class finished the task and he went through all of the slates. Most of the answers were wrong because people have made silly bits of arithmetic mistakes on the way. And he got to that last chalkboard that Gauss put down very first of all. And there on the chalkboard was the correct answer, 5,050. And the teacher was completely taken aback and asked the young Gauss to explain, well, how did you come up with that answer without doing any of the hard work that I thought you would have to do? And Gauss said, well, I found a shortcut to how to do this. Rather than starting at the beginning of the journey and just counting through the numbers from 1 to the 100, what Gauss did was kind of lift himself out of the journey that was being set and said, okay, well, let's look at the beginning and end of the journey. Well, 1 plus 100 is 101. 2 plus 99 is also 101. 3 plus 98, 101. So what Gauss saw was that in taking the pairs of numbers from the end and going through to the middle, you have 50 pairs of numbers adding up to 101. So the answer was clearly 50 times 101, 5,050. And that's the reason that Gauss was able to write down the answer so quickly. He found this clever way of looking at the problem, which just shortcut any of the hard work that his teacher was expecting him to do. And when my teacher, my maths teacher, Mr. Baleson, told us this story and said, that's what mathematics is about, the art of the shortcut, I fell in love with this subject and decided that, yes, this was a subject I wanted to learn. I wanted to learn about these shortcuts that we've amassed over 5,000 years of trying to find clever ways to think about problems. And so my book is kind of your shortcut to all of these shortcuts that have taken us 5,000 years to put together. Now, it's interesting because Aristotle talked about different sorts of work. And you might say, well, hold on, I actually enjoy working. And I certainly enjoy working as well. But it's the sort of work you want to do that's important. I want to do work that I value for its own sake, work that I enjoy doing. I enjoy trying to find these mathematical shortcuts, even if it might take me a long time to discover them. What I don't like is just work for the outcome, where I might have to do a lot of hard work just to achieve an outcome. So Aristotle actually had two names for this. Praxis, that's the work we love and enjoy doing. Proesis is the work for outcome. So what I'm trying to give you is a suite of shortcuts will enable you to get to the work that you really enjoy doing and avoid just the hard slog of proesis sort of work. And actually, Karl Marx always said that the whole point about communism is not to eliminate work. In a higher phase of communist society, labor has become not only a means of life, but life's prime want. So what I want to do is to show you a little journey through some of the shortcuts that I've talked about in this book that hopefully will give you your signposts to be able to get to the work that you perhaps really enjoy doing. So we're going to start actually with some shortcuts not really created by mathematicians, but created by nature itself. Nature is actually very good at finding shortcuts to kind of hard problems. For example, if you take a bumblebee, the honeycomb that a bee makes, you've got these lovely hexagonal shapes that the bee makes in the beehive. Now, why didn't it make squares or triangles? Well, it turns out that this is really the shortcut of using the smallest amount of wax to contain the largest amount of honey. So it turns out that the hexagon nature has discovered is the shortcut to using as little wax, which actually is very expensive for a bee, in order to create that honeycomb. So nature very often hones in on these very efficient ways of solving a problem. Bubbles is another interesting example. So the reason that when you blow a bubble, it's a sphere, is because actually the sphere is the shape with the smallest amount of energy, which contains that particular volume of air. So if you take any particular frame and you put a bubble over it, nature finds the shape which is the least energy shape. And this actually has been used by humans in architecture, for example. So this is Otto Frei's building at the Munich Olympics, and he actually used bubbles to create this structure, which he knew would be it would be to stand up, it would be energy efficient, it would be a way of creating a beautiful kind of canopy without too much tension on the surfaces. And so quite often what we humans have done is to understand clever shortcuts that nature has come up with, but then we can use that to come up with our own shortcuts. And there's a kind of sort of a thesis in science, which is actually goes back to Maupertuis, and it said in everything nature is thrifty. In a way, nature is very lazy, like me as a teenager, a very lazy teenager, that nature hones in and finds the efficient shortcut to a solution very often. And this is perfectly illustrated actually in this particular challenge. So in the book, I've got a few puzzles for you to try and tease out the beginning of each chapter, a puzzle which challenges you to try and find the solution to a problem. Here's an interesting puzzle. If you've got a lifeguard who's on sand and has to swim out to sea to rescue a drowning swimmer, and for example, suppose you can run twice as fast on sand as you can swim on sea, then what's the most efficient path in order to be able to get to the swimmer that's drowning? So this again is, what's the shortcut? I could run as much along the sand as possible and then have the shortest bit into the sea, but that probably isn't the most efficient way. And it turns out that nature has already solved this problem, because we can actually set up the same problem with light. Light always finds the shortest path from A to B. So the sand and the sea is a bit like air and water. The light travels at a different speed through air and water, just as the lifeguard runs at a different speed over sand and sea. And so we get this kind of idea of this refraction of the light, and this is gives you the effect of looking like your legs have shortened when you look at yourself when you're in a swimming pool. So nature's already found this solution, but how do we find that solution? Suppose I mean, we could set up two things which have the same speed as light as the lifeguard over the sand and the sea. But actually we have come up with this very clever tool which helps us to do what nature seems to do naturally. It's one of the tools that we came up with during Newton's age, the calculus. The calculus gives us a way of finding the minimal journey here from the lifeguard to the swimmer at sea. And it tells us with this very clever tool what the point is that we should enter the sea in order to get to the swimmer as quickly as possible. So this tool of the calculus has given humans a sort of almost a conscious, articulate way to do what nature has been doing very often naturally. Again, the same tool help us understand those bubbles, for example. And see, one of the challenges, for example, you might want to find a curve which gets you on a roller coaster ride as quickly down to the bottom as possible. And this was one of the challenges in Newton's age, to find what is the curve that gets you from A to B the quickest possible if you're just rolling a ball down it. And we use this tool of calculus to analyze all the different curves. And it turned out it was a very kind of interesting curve. If you take a bicycle wheel, for example, and put a pen on that bicycle wheel, will the wheel along the surface and see what the trajectory is that's drawn out by the pen stuck on the side of the wheel. This particular curve turns out to be the solution which calculus will identify for you as the fastest way to get from A to B if you turn it upside down on a roller coaster ride. So nature has given us some ways to find shortcuts, but we actually needed the language that Newton and Leibniz came up with, the calculus, in order to often to understand these kind of efficient, fast shortcuts that nature often comes up with. One of the challenges actually going forwards that we're all going to have is the challenge of our modern age is that it's an incredibly data-rich world. So another of the shortcuts I talk about in the book is how are we going to navigate this kind of modern world which has so much data in it that we seem to be just overwhelmed by the amount of data. And we really need shortcuts to just say, well, I don't need to look at all of this data. I just need to identify a small amount of it in order to be able to understand what's going on in this world. And one of my favorite uses of kind of mathematical shortcuts to understand what's happening in a data set was one that was to do with an advert I used to watch as a kid. There was a kind of, this is like the 70s, there was a cat food advert for Whiskers, and in the advert they very boldly claimed, in tests, 8 out of 10 owners who expressed a preference said their cats preferred Whiskers. And I thought this was very curious because we had a cat, and I don't remember anybody coming around and asking our cat or us what sort of cat food it preferred. So I was always rather curious as a kid. Well, how come how many people did they have to ask in order to be able to be confident that that claim that 8 out of 10 cats prefer Whiskers? And when it came to university and I started to learn some of these tools of data analysis, I was quite shocked actually to find out that actually you don't really need to ask that many cats to have confidence in that kind of claim. So this is the point. You've got a population of cats or people, and you want to have some idea about their preferences, for example. What's the kind of size of sample I need to have in order to be able to be sure that I can make a claim like 8 out of 10 cats prefer Whiskers? Well, you see, I don't mind if I've got a little bit of error in the 8 out of 10. Maybe I'm allowed 5% either way, so 8.5 or 7.5. I'm happy with that. And maybe I'm also happy with saying, okay, well, my sample, I want it 19 out of 20 times to be representative of really what's happening in that population. So with those kind of two little rough edges on our estimate, turns out that, you know, how many cats are there in the UK? There are 7 million cats, it's estimated. How many of those cats do I need to ask in order to be able to be pretty confident that 19 out of 20 times I'm going to be within 5% of the real preferences of those cats? Well, it turns out that you only need to ask just under 250 cats, and you can make that sort of claim about 7 million cats. And I think that's a pretty unexpected and quite extraordinary. And that's very useful to know, because you might say, well, you know, in order to be able to make that claim, perhaps I need to ask all 7 million cats. No, actually, you can get away with a shortcut and actually ask only 250 cats, and you can be confident that what you're getting from that small population is 19 out of 20 times within 5% of the true value. So I think that being able to know how much data to look at before you know really what's going on in your data is going to be a very powerful shortcut going forward. And this is particularly relevant, for example, in our current climate of artificial intelligence and machine learning. We really need to know how much data does an algorithm need to be given before it really has a chance of learning what's happening in sort of a huge amount of data such that they can be then let loose on, for example, identifying cats as opposed to dogs. How many images of cats do you need to give vision recognition software before it can be pretty confident about identifying a cat rather than a dog? But there are kind of other cases where knowing the amount of data you need to look at before you make a decision is quite important. Actually, one of them is in kind of game show scenario. Some of you may know this this game show, Deal or No Deal, where there are 20, well, in this case, 26 boxes. Each one contains a particular sum of money, and you open the boxes in turn, and then you have to make a decision about which box you're going to stick with. Now,